Hello, everybody, and welcome to your channel Thermal Engineering Concept and Principle. This is Professor Ali Tarrad. In this episode and series of different videos, we will talk about an application in the field of thermal engineering, which is the most important application in our heat transfer topic. What are the structural components of shell and tube bundle, heat exchangers, and how do they work? In this series, we will talk about this type of heat exchangers and how can we predict the thermal design of such heat exchangers. Hello, everybody, and welcome back to your channel, Thermal Engineering Concept and Principle. To continue our videos about thermal design of heat exchangers and specifically the shell and the tube heat exchanger, in this part we will present the prediction of shell side heat transfer coefficient. How can we predict or estimate this value for a fluid that is flowing on the shell side? And of course, the fluid doesn't experience any change in its state. I mean, there is no condensation or evaporation. So it's for a single phase fluid. And thank you for your support. And let us go to the objectives of the present video. The objectives of the present video cover the procedure on how can we predict the heat transfer coefficient on the shell side. That is a step-by-step procedure. And then we will introduce a practical case study and how can we calculate the heat transfer coefficient of fluid that is flowing on the shell side. And finally, we will arrive to the summary of the content of the present video. Simplify the procedure for heat transfer coefficient prediction on the shell side. Of course, the procedure which is presented in the present episode is already published in different textbooks. You may find it, but I have put it in a simplified form where it is possible to be computerized, or even for a single the heat exchanger design, you may follow these steps. First, we have to estimate the cross-section flow area on the shell side for the fluid. A sub CS, A sub C refers to cross-sectional area, and the subscription S refers to the shell side. We have P sub P, which represents the tube pitch, and D sub I shell means the inside diameter of the shell. L sub B refers to the um, distance between uh, baffles, and D naught refers to the outside diameter of the tube. Then we may calculate the mass velocity of fluid, G sub S, which is represented by the mass flow rate on the shell side divided by the cross-sectional area. From that, we may estimate the linear velocity of the fluid, U sub S, and then we may go to estimate the equivalent diameter, hydraulic diameter on the shell side. We have two cases for square tube layout. It is represented by this equation. And for equilateral triangular tube layout, that is 60-degree in the for the angles between these heat exchangers, these tubes, and it is estimated by this equation. Once we have calculated these parameters, we may go to estimate the Reynolds number on the shell side as described by this equation. And once we have estimated the Reynolds number, we may go to estimate the heat transfer factor from this graph, which is presented in terms of Reynolds number and the baffle cut percent. Then we will get the heat transfer factor. The heat transfer factor can be used to estimate the Nusselt number, one of these equations. So to estimate the Nusselt number from the knowledge of the heat transfer factor and Reynolds number, a general form is presented by this correlation, where we have the last term to introduce the effect of change of the viscosity, dynamic viscosity due to the change of temperature between the bulk fluid and the fluid adjacent to the tube wall. From the knowledge of H Nusselt number, we may estimate the heat transfer coefficient on the shell side. For the last term of the above equation, if the dynamic viscosity doesn't change a lot with the variation of temperature, it can be dropped from the above equation, and Nusselt number will be estimated in terms of the heat transfer factor, Reynolds number, and the Prandtl number to power 1/3. Now, let us consider a practical case study where we have a water flow rate of 3,000 kilogram per hour. It passes on the shell side of a shell and tube heat exchanger, where the tubes are arranged in a square layout with a tube pitch of 1.25 times the outside diameter of the tube, and the tube is 3/4 inch or 19.05 millimeter. The tubes were accommodated in a shell as presented as a 12-inch schedule 40S stainless steel pipe, which has inside diameter and outside diameter as shown in these values, and we need to estimate the heat transfer coefficient when the baffle spacing is 0.25 meter and a cut of 25%. We have all the properties of the uh, fluid that flows on the shell side, which is water, and we have a Prandtl number equal to 5.85. The solution for this equation, we may follow the same procedure as mentioned above in the previous slides. First, we have to calculate the tube pitch, 1.25 d naught, which is equal to 23.81 millimeter. We have the cross-sectional area, depending on the buffalo spacing, inside diameter of the shell, outside diameter of the tube, and the tube pitch layout. Then we have, if we substitute these values, then we will get uh, value of the cross-sectional area to be 0.01524 meters square. Then we may go to estimate the mass velocity depending on the mass flow rate, which we have mentioned it as 3000 kilogram per hour. Then G shell side equal to 54.68 kilogram per meter square second. This will give us a flow velocity of 0.055 meter per second, and we may use this value with the help of the equivalent, and we have a square tube pitch or tube layout. Then we have the equivalent in this form of equation. If we substitute the values, then we will get the equivalent diameter of the shell side to be 18.8 millimeter. That is the equivalent diameter of the flow area, and that will lead to a Reynolds number depending on the properties and physical dimension of the equivalent diameter to be 1195.5. If we use this value with the aid of the chart to get insult number, of course, we will neglect the last part of the last term of the Nusselt equation to neglect the effect of viscosity change with temperature, and then we will go to the final form of this equation as Nusselt number equal to a transfer factor times Reynolds times Prandtl to power 1/3. Of course, the heat transfer factor J sub h depend on Reynolds number, and if we go back to the chart, then we will get J sub h on the shell side equal to 1.8 times 10 to power minus 2, and Nusselt, if we substitute these values, then Nusselt will be equal to 38.77, and with the help of thermal conductivity on the shell side of the fluid and the equivalent, then we will get the final value of heat transfer coefficient to be 1266.3 watt per meter square Kelvin. This figure shows the layout of the tubes, that is 90-degree square tube layout with the values of d naught, p sub t of the tube pitch. And finally, we may have a look at this figure where it shows the shell diameter, the buffer spacing is equal to 0.25 meter, and the buffer cut, which is 25% of the inner shell diameter. And in general, a buffer cut between 20 and to 25%. It provides acceptable the heat transfer coefficient and minimal uh, pressure drop. And in general, the spacing between baffles as a minimum to be 50 millimeter, or in general, we may use 20% of the inner diameter of the shell. This is the final form of our example. Conclusion remarks about our previous case study. We may control the heat transfer coefficient and the pressure drop on the shell side by controlling the distance between baffles. When we go to a direction of reducing the baffle spacing, that will lead to increase the fluid velocity and hence Reynolds number, and finally we may obtain higher heat transfer coefficient, while also that will increase the fluid pressure drop. On the contrary, if we increase the buffer spacing, in effect we are reducing the velocity on the shell side, reducing Reynolds number, and as a final result, lower heat transfer coefficient will be obtained and reducing the fluid pressure drop. So in general, the thermal design of heat just is a sort of art where the designer should control his parameters to obtain the optimum design, and it should be effectively uh, conducting the heat transfer process. And we may describe more with the upcoming episodes about this subject. Uh, of the content of the present episode. We passed through a step-by-step procedure or method on how to predict the shell side heat transfer coefficient for a single phase fluid. And then we gave a case study with some conclusion remarks on the application of the procedure to obtain the heat transfer coefficient of the shell side. We have some resources. You may go and get them through a link will be presented in the description box of the present episode. And thank you for watching, listening, and your continuous support. If you find the content of the present episode is useful to you and others, please subscribe to the channel and share this information with your colleagues or your network. I will introduce more topics about the use of heat transfer technology, the application in heat changers in the upcoming episodes. Bye bye.